This question is comparing Coulomb's law, the force of electric attraction, with the Universal Law of Gravitation. And we can look at this, and if you've read through this section or read through the note, there's a bit of a comparison between these two. These two look like quite similar, these two equations. They're both force, they both have a constant g or k, they both have two quantities that are multiplied together, they're both divided by a distance squared. So they look quite similar. So they have some similarities. They also have some differences as we go through it. So note those as you look through the note. Just kind of be aware of those. We're going to go through and we're going to solve this. A couple of things that we are kind of given, I guess, before we sub into this. We know what K is. K is this Coulomb's constant. It is 9 times 10 to the 9. That is Newton meters squared per Coulomb squared. That's just a constant. It would be on your equation sheet, and we'll just use that. This thing mentions that it's the charge on that we're talking about here. These Q's are charges. Q1 is, let's say, the electron. Q2 is the proton. Protons and electrons both have the same charge. So this is 1.6 times 10 to the 19 coulombs. You could say that's true for Q1. It's also equal for Q2. They both have the same charge. Last thing is this distance. So R, the separation between it's actually the separation between the centers of the two objects. When they say 1 nanometer, this nm is 10 to the minus 9 meters. Okay, so those are our numbers. After that, it's just a matter of subbing in. So this is fairly easy. Q1, 1.6, 10 to the minus 19. Q2, same thing. That's a 10 there. 1.6 times 10 to the minus 19. Our number on the bottom is 1 nanometer. And don't forget to square it. Okay, so whatever number you're putting on the bottom is squared. We multiply all this out, and we're going to get approximately 2.3 times 10 to the minus 10 newtons. This is an attraction. We know that an electron and a proton are attracted. So when we go through and use this, your textbook kind of mentions we're going to sub in magnitude only for these. So you might notice that the electron and the proton have the same charge, which they do. They're the same magnitude of charge. Electrons, of course, are negative, protons are positive. I'm not going to sub in any signs. I'm just going to get a number, and then I'm going to imagine, let's draw it up here. There's my electron, over here is my proton. They're separated by this 1 times 10 to the minus 9 meters. Okay, this distance between them. But I know that opposites attract. Okay, so negatives and positives, this is going to be an attraction. And there is my force. We were actually told in the question it was an attraction, so I don't really need that direction. I'm just really looking for the magnitude, but it is an attraction. So Coulomb's law can either be an attraction or a repulsion. Gravity, on the other hand, is always only just an attraction. So a couple numbers to remember. Again, this is on your equation sheet. 6.67 times 10 to the minus 11. What would that be? Newton meters squared per kilogram squared. I think that would be. Mass 1. We need to know the mass of an electron. So let me see, what is that? That is this number, 9.1 times 10 to the minus 31 kilograms. Mass of a proton, 1.67. These numbers are on your equation sheet as well. Distance between them, same distance that we had before. Sometimes you'll see it written as an R, sometimes you'll see it written as a D. Doesn't matter. Same idea. We're going to sub into this thing. So FG is G, 6.67 times 10 to the minus 11. Mass 1, 9.1, 10 to the minus 31. Mass 2, and distance between their centers. And again, don't forget to square it. So as you put all this stuff into your calculator, don't forget to hit that squared button for this bottom part. Here we are going to get 1.0 times 10 to the minus 49 newtons. Also an attraction, always an attraction in the case of gravity. But we'll write it anyways. This is small, 2.3 times 10 to the minus 10, that's a small quantity. This is very small, okay? Anything times 10 to the minus 49 is very, very small. The reason that this thing is so small is because this constant in the force of gravity equation is times 10 to the minus 11. It's very small, whereas this number is relatively big. I know that's not a big quantity, but it's still relatively big. It's big because this constant in this equation is a positive exponent. So it's quite a big constant. So one of the things as we look through these two equations, they're very similar. They have a lot of things that are the same between them, or at least similar. People talk about the electric force being a much stronger force and gravity being a weak force because of the difference in those constants, and we can kind of see that played out here.